In this video, we're going to talk about section 7.1 in our book, Integration by Substitution. Substitution is a really powerful technique of integration. So it's a way of trying to go the other direction from the chain rule. So if you recall the chain rule, the derivative of a composite function, f of g of x, we take the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. So now if we turn around and integrate this result, so here's our integrand, then we're going to try to find our way back to how to get to our original composite function. So in this technique, what we're going to do is we're going to try to recognize what is that inside function. And we are going to call that u of x. So that's our substitution. We're going to call u of x equal to g of x. Or more specifically, we'll just shorten it up and say u is going to be that inside function. Then we're going to take the derivative of u with respect to x, and that's going to be our g prime of x. We'll then we'll multiply this dx to the other side and say du is going to be g prime of x dx, and then solve for the dx and say dx is going to be du over g prime of x. So then we revisit our integral, and we're going to rewrite that. Instead of having x as the variable and dx as that differential, we're going to get our new integral, and we're going to call that f prime of, and then here's going to be our u. So we're going to replace the g of x by u, and let me change that color to a green color because I want you to see the u. And then we'll have this g prime of x that we'll leave there momentarily. And the dx that we see, the dx here, we're going to replace by du over g prime of x. So that's going to become times du over g prime of x. That will allow us to get rid of or account for that g prime of x. Now sometimes that's not a perfect fit, but as long as we can cancel everything except for perhaps a constant, we're going to be okay. So the new integral that results is going to be the integral of, and we'll call it f prime of u du. So this, in some words, in math language, it would be considered a change of variable. So we've changed from the x's and dx's to u's and du's. So then, hopefully now this integral is going to be doable. And so we'll say, oh, the antiderivative of f prime of u is going to be f of u, and then plus our constant of integration. And then we'll go back and replace our u, which, remember, we said that u was going to be g of x, and so we'll go back and call that f of g of x plus any constant. And so that's the way we're going to kind of work our way backwards using from the chain rule. So let's see some examples and see how this works. I think you'll get the hang of it once we do some. But it's a little tricky when you get started, and hopefully we'll get better at it with practice. So when you look at the integral of cosine of 5x, what your first challenge is to say, what is the inside function? So what function is inside another function? And hopefully we can see that our inside function is going to be 5x. So that's going to be our substitution. We're going to call u 5x. Then we have to compute du. Now this is du over dx, but we're going to kind of shorten it up and multiply the dx over already. So we'll take the derivative of 5x, which is 5. So that's du over dx, and then in the same step, we're going to multiply the dx to the other side. So I'm just going to write it off to the side. We're saying du dx is equal to 5, and then we're going to multiply that dx to the other side. Then we're going to solve for that dx, because that's what we want to replace in our original integral. So the dx is going to be du over 5. Okay, now we're ready to do our substitution. So we're going to take our integral, and it'll still be cosine of, the 5x is going to be the u, and that dx we're going to replace by du over 5. Now, this 5, remember, is just a constant, so we are okay to pull that constant all the way outside of the integral, where it will just wait. And now the integral that we're left with, the integral of cosine of u du, this we can do, because we know that the function whose derivative is cosine is sine of u. The 1/5 still is there, and our constant of integration is added in. Then we go back and say, since we originally said that u was 5x, we're going to get 1/5 times the sine of 5x plus a constant. And just to make sure we see it, so if this is our original function, which we are, this is our integral, then your check, remember, is to differentiate this and see if we don't get back that same integrand. So to take the derivative, the 1/5 would hang out. We would take the derivative, this is a chain rule derivative, the derivative of sine is cosine of, leave the inside function alone, times the derivative of the inside function, and the derivative of the constant is 0. Our 1/5 and the 5 will cancel, and we get to just cosine of 5x, which is exactly what we wanted. That's that integrand. Okay? All right, let's try another one. So let's say that, can you see what the inside function is? And sometimes this takes some trial and error. You don't always get it on the first try. But here, hopefully we can see the 6x plus 5 is inside the square root function. So du, its derivative, is going to be 6 dx. The dx is going to be du over 6. So our integral is going to become the square root of u, and the dx is going to be replaced by du over 6. So we can't integrate if we have u's mixed in with x's. That's not viable. So we can't go forward until all of the x's have been replaced either by something with u or a du or some constant. We can pull the 1/6 all the way outside the integral, and I'm going to rewrite the square root of u in a more integral-friendly form as u to the 1/2. We'll add 1 to the exponent, making that 3/2. We're going to multiply by the reciprocal using our power rule, and the constant is waiting in the wings to join the fun. We can cancel the 2 with the 6, and so the 1/3 times 1/3 will make that 1/9, and we are going to go back from the u to the original 6x plus, I think that was, plus 5 to the 3/2 plus c, and that is our answer, our indefinite integral. Okay, so a lot of times when you have an exponential, the u is going to be what's in the exponent. So in this case, we're going to try u is x cubed. That makes du 3x squared dx. This is good news because notice we're going to pick up that other x squared power. And as long as we can get the right power, the constants we can work with. So solving for dx will give us du over 3x squared. So our integral is going to become x squared. That's going to be e to the u. That accounts for our e to the x cubed. The dx we will replace by du over 3x squared. This is good news because the powers of x are accounted for. We have an extra 3 in the denominator, but constants are easy to fix. We can just pull it through, and our integral becomes one that we can do. The integral of e to the u is just e to the u. The 1/3 is still there, and we get our constant of integration. We go back and plug in our substitution. U was the x cubed, and that is our indefinite integral. Okay, on the next one, a lot of times with fractions, it's a good practice to try to say u is the denominator. That is going to make du be, in this case, just 1 times dx is dx. So du is just dx. So we get 1 over u, and the du is replaced by dx. So this is an integral that is sometimes tricky when you're starting out, but the integral of 1 over u is the natural log of the absolute value of u plus our constant of integration. And going back and replacing the u's by the x's, that makes that be the natural log of the absolute value of x minus 5 plus c. Let's scroll up a little bit and try a couple more. Now this one, you can see here that if we picked u to be cosine, du would be a negative sign, but we can't account for that power. If we pick the inside function, u to be the sine of x, and then we can see that's going to be u to the 4th, the du is going to be cosine of x dx, and so the dx is going to account for that extra cosine x we have in our integrand. So our integral becomes the cosine of x. That sine to the 4th we're going to call u to the 4th, and the dx we will replace by du over sine of x. We can see that du over cosine of x. I didn't say that right. Let me try that again. So that's going to be du over cosine of x. Whew, that's better. The cosine of x's will cancel, and so our integral becomes u to the 4th du. We're going to use our power rule and add 1 to the exponent, multiply by the reciprocal of the new exponent, and we'll get a constant of integration. And then we'll go back to our original x version. So u was sine x, so that's going to be sine to the 5th of x plus the constant of integration. Okay, now on the next one, this is the first time or two you see this. This can be a little tricky. The inside function looks like it's going to be that 1 over x, and that is actually the right choice, which we can think of for derivative purposes as x to the negative 1. So that means its derivative is going to be negative x to the negative 2 dx, which we might want to think of as negative 1 over x squared dx. To solve for the dx, we're going to multiply by a negative x squared to the other side. So dx is going to be negative x squared times du. Does that make sense? So our integral is going to become secant squared of u. There's our 1 over x. We're going to leave that x squared there for a moment, but when we replace the dx by a negative x squared du, we can see that this is just what we needed, because it's going to account for that extra x squared we had in the denominator. The negative sign can get pulled all the way through the integral, and we're ending up with the integral of secant squared u du. Hopefully we remember the derivative of a tangent is secant squared, therefore the integral of secant squared is going to be tangent. We've got that extra negative sign, so that's going to be a negative tangent of u plus c, which we are going to call negative tangent, going back to the x's, of 1 over x plus c is our final answer. Okay? Sometimes you just have to see some of these before you kind of see what your options are. So here, again, when you have a fraction, a good place to try, especially since you can see the numerator is a degree 1 less than the denominator. That's going to be something we'll talk about more in the future. So that means a good try, it'd be let u be the entire denominator. That means its derivative is going to be a 3x squared dx. That's good because that's going to account for that x squared in the numerator. And solving for dx will give us du over 3x squared. So our integral, we're going to leave the x squared up there for a moment. The denominator, that whole denominator is just u. And the dx, we're going to call du over 3x squared. This is going to work because we can account for all of those powers of x and pull the extra 1/3 out, and it becomes an integral that is going to become more and more familiar, 1 over u du. So the integral of 1 over u is the natural log of the absolute value of u, and then we'll go back to the x's instead of the u's and get x cubed plus 2 in absolute values plus c. And there's our indefinite integral. Now the green one is a little interesting. It can be challenging the first time or two you see it. The inside function, we see that these square roots are inside the cosecant and the cotangent. And so we actually want to call u square root of x, which we can think of for derivative purposes as x to the 1/2. That's going to make du 1/2 x to the negative 1/2 dx, or it might be easier to look at that, I don't know, as 1 over 2 square root of x. So the negative 1/2 power goes into the denominator with the 2 from the 1/2, and the 1/2 power is a radical. So to solve for the dx, we're going to multiply the 2 square root of x over to the du side. Then our integral is going to become cosecant of u, cotangent of u. That square root of x in the denominator is going to be canceled with the 2 square root of x du, that is our dx. So that will take care of that extra square root of x. So now the 2 can get pulled all the way through, and our integral no longer has x's and u's mixed together, which is good. If we remember, the derivative of cosecant of u is negative cosecant cotangent. That means the integral of cosecant cotangent is going to be a negative, and the 2 is still there, cosecant of u, whoops, got carried away with the u, cosecant of u plus c, and then going back to the x's, that's going to be the negative 2 cosecant of the square root of x plus c. Okay, there's another thing we have to talk about, concept that has to do with this U-substitution, and that is how are we going to do definite integrals. So I'm going to show you 2 different ways of evaluating these, and you can choose either way if you're going to get a final answer, if you're just trying to get the final answer, and that's the main purpose. But you're going to have to understand the second way that I talk about when we talk about changing the limits from x limits to u limits, because they may force you to do that on an AP exam multiple choice question. So in this case, there's actually also 2 ways to do it depending on what you choose as your u. So there are actually 2 different u's that will both work. So I'm going to show you here two ways to deal with the limits and also two different ways to make a U-substitution. So here is one way. So we can say that U is the tangent of x, then du is going to be secant squared x dx. And that means the dx is going to be du over secant squared x. Our integral is going to become, the tangent is going to now be u. We have our secant squared x, and the dx is going to get replaced conveniently by du over secant squared x. And these are going to cancel. Now you will notice I have not written the limits up here, and that's not because I just forgot. It's because where it stands right now, those limits are x limits. So they are valid when our variables are x's. They are not going to be correct when we have changed the variable to a u. So don't write them yet, because if you do, that's actually incorrect. And if you do that on an AP exam question, you'll lose a point. So in this case, what I'm going to do is go ahead and do the antiderivative first. So using our power rule, we're going to add 1 to the exponent, multiply by the reciprocal. Then we're going to go back to the x's. So that's going to be 1/2. U was our tangent. That's going to be squared. Now that we're back to x's, we can bring back our x limits because these are going to be correct if we have x's. So that is going to, I'm going to scroll up because I'm going to do the other way on the other side. So this is going to be 1/2, and we're going to get tangent squared of pi over 3 minus 1/2 times tangent squared of 0. Okay, now here we go. 1/2 tangent of pi over 3 is going to be sine pi over 3 over cosine of pi over 3 squared. And since the sine of 0 is 0, tangent of 0 is also 0, so that second part's going to go away. Well, let's see what we've got. 1/2, the sine of pi over 3 is going to be square root of 3 over 2. The cosine of pi over 3 is 1/2, and then we're going to square that. So that's going to be 1/2, and the 2's are going to cancel. Square root of 3 squared is going to be 3, and so our final answer is going to be 3/2. So that's method 1. Now I'm going to come back and I'm going to do the same integral, but I'm going to do it a second way. Now it's going to be different in two respects. I'm going to pick a different u for the substitution, but more importantly than that, I'm going to deal with the limits on this definite integral in a different manner. So in this, if you're, I don't know if you recognize it, different people see this differently. So if we see that integral of tangent x secant squared as tangent x times secant x times secant x dx, then if we choose our u to be secant x, the du, the derivative of secant x, is going to be secant x tangent x. It'll account for the rest of that integrand. So I'm going to choose u to be secant x. That will make du be secant x tangent x, and then the dx at the end. So the dx is going to be du divided by secant x tangent x. So our integral, and this integral is also going from still 0 to, what did we say, pi over 3. So we're going to call that tangent x secant x times, we're going to call that second secant x u, the dx is going to get replaced by du over secant x tangent x. And can you see that's going to cancel? And so our integral is going to be the integral of what's left, u du. Now we're going to change our limits to be u limits. So we're going to call that u of 0 and u of pi over 3. So since our u is secant x, u of 0 means secant of 0, and secant of 0 is 1 over cosine of 0, and cosine of 0 is 1, so that makes our lower limit 1. See how that worked? And the upper limit is going to be u of pi over 3. So that's going to be the secant of pi over 3, which is 1 over cosine of pi over 3, which is going to be 1 over 1/2, which is 2. So our integral becomes the integral from 1 to 2 of u du. So now our integral of u, we're going to use our power rule. So that's going to be u to the second, and we'll get a 1/2. Now, because we have changed our limits, we don't have to go back to x's. We can go right to evaluating at those u limits. And so that is going to be 1/2 times 2 squared minus 1/2 times 1 squared. So 2 squared is 4, half of that is 2, 1 squared is 1, times a half is a half, and you can see we get the same answer we did the other way. So you'll get to the same result. Now, for 90% plus of the time, it doesn't really matter which way you do it, but you absolutely must know how to do this, because in the past, they have sometimes tested your knowledge of substitution and changing those limits in multiple choice questions. So you might be given some integral like this, and your choices will be not worked out all the way to the end, but they will be a bunch of different integrals with different limits, and you will have to be able to recognize which integral has the correct limits that go with the substitution. So it's a must-have skill. So let's do this on the second one, and I'm sure you can do this, when you just do the integral, go back to x's and then plug it in. So let's practice these by changing the limits. So in this case, our u, hopefully you can see this, is going to be 2x. The du is going to be 2dx. So the dx is going to equal du over 2. We're going to make this the integral of secant squared of u, and we'll get du over 2 for that dx. We're going to change our limits to u of negative pi over 8 and u of pi over 8. So let's see, the 2 in the denominator is going to come through and be 1/2. U of negative pi over 8 means we're going to get u of 2 times a negative pi over 8 is going to be a negative pi over 4. And similarly, u of pi over 8 is going to be 2 times pi over 8 is a positive pi over 4. We'll get secant squared u du. So the integral of secant squared, the function whose derivative is secant squared, is tangent. We'll leave the 1/2 in front, the constant. Because we have changed our limits, we do not have to go back to the x's. We're going to go right to plugging in those u limits. So that's going to be 1/2 tangent of pi over 4 minus 1/2 tangent of a negative pi over 4. So that will be 1/2. Now, tangent pi over 4 is sine pi over 4 over cosine pi over 4. but pi over 4 is where sine and cosine are both the square root of 2 over 2. And so square root of 2 over 2 over square root of 2 over 2 is going to be 1. So that's going to be 1/2 times 1 minus, now negative pi over 4 is going to be in quadrant 4, where the sine is negative but the cosine is positive. So that's going to be a negative 1. And so we're going to get 1/2 plus 1/2, which is 1. And that's going to be our answer. Okay, let's get one more practice changing these limits. I'm back. I actually accidentally bumped it with my left hand. So we're going to say the inside function, I'm going to bring my pen back up. The inside function u is going to be x plus 1. So du is going to be just dx. I'm doing this at home in front of my fire. Can you hear the fire popping in the background? So this is going to be the integral of the square root of u du. And we're going to change our limits to u limits. So that's going to be u of 0 and u of 3. So u of 0 is going to be plug in 0 for the x is going to be 1. And u of 3 is going to be plugging in 3. We'll make that be 4. So it's going to be the integral from 1 to 4. The square root of u, I'm going to write as u to the 1/2 du. Adding 1, using our power rule, adding 1 to the exponent is 3/2. The reciprocal is 2/3. We're not going to go back to x's because we changed our limits to u limits. So we're going to get 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. So when we're doing the 3/2 power, we can take the square root of 4, which is 2, cube that, which is 8, times 2/3 is going to be 16/3. 1 to any power is 1, times 2/3 is 2/3. And 16/3 minus 2/3 is 14/3. And you're free to leave it as that, or if you prefer, you can give it a mixed number. I think that would be 4 and 2/3. Those are equally acceptable. All right, almost done. Here's a couple that are really tough, maybe 4 that are really tough. So the first one, it's hard to see what this U-substitution is. But let's go with the inside function being x plus 4. So if we say u is x minus 4, then du is going to be dx. So as we go to make this substitution, we got x we don't know what to do with. That's going to be a square root of u, and that's a du. Now, the problem is we can't continue here because we've got this x mixed in with our u's, and that's not viable. So somehow we got to figure out what to do with this x. So the trick is when you look back at your U-substitution, you can see from here that x, if we add the 4 to the other side, is actually u plus 4. So we are going to replace that x by a u plus 4. I'm going to think of that square root of u as u to the 1/2 du. Now everything's got u's in it. There's no x's remaining. I'm going to distribute that u to the 1/2. And so that's going to be u to the 3/2 plus 4u to the 1/2. And there's our du. Now we can use our power rule. So we're going to add 1 to the 3/2. That's going to be 5/2. Multiply by the reciprocal of the new exponent, plus add 1 to the 1/2 to get 3/2. We're going to have the 2/3, and that's going to have to multiply the 4, and then we're going to add in our constant of integration. So I'm going to clean up and also go back to the x's. So u, remember, was x minus 4 to the 5/2. This is going to now be 8/3 times x minus 4 to the 3/2 plus our constant of integration. Those are sneaky. Got to be on the lookout for those. The next one is a tough one too, because it's going to force us to, if we try to make a U substitution, the problem is if we say U is tangent, then du is secant squared, and there's no secant squareds to be found. So when you hit the wall like this, especially with trig functions, we have to think about maybe a clever trig substitution. So we'll go back to our most famous of all trig identities, sine squared plus cosine squared equals 1. Now we recognize that tangent squared has cosines in the denominator. So if we start with our favorite trig identity and divide by cosine squared, we'll get an identity that's pretty useful. So the sine squared over cosine squared is tangent squared x. The cosine squared over cosine squared is 1, and the 1 over cosine squared is secant squared. So solving for tangent squared, we can see that tangent squared x is secant squared x minus 1. This makes all the difference, because now our integral, if we replace the tangent squared by secant squared x minus 1, this we can do. Since we know the integral of secant squared is tangent x, and the integral of 1 is x, we get tangent x minus x plus c. So keep that in the back of your mind. If you run into some kind of integral with trig functions and you have no idea, see if there's a clever trig substitution we can make, a clever identity involving trig functions we can use. It's going to come up on this one too a little bit. Same issue here, sort of, that we had before, in that if we try to say u is cosine x, du is going to be sine x, and there's no sine to be found. So the clever trick here is to think of that as cosine x times cosine squared x. This we know from our favorite trig identity of all time, that cosine squared x is actually 1 minus sine squared x. So we can, in this integral that wasn't going anywhere, we can replace the cosine squared by 1 minus sine squared x. Now this breaks everything loose. If we distribute that cosine x, we're going to get a cosine x, and then we'll get a minus cosine x times sine squared x dx. The first integral we can just do directly. The integral of cosine is just sine. On the second one, we can say let u be sine x, then du is cosine x dx, and dx is going to be du over cosine. So that integral will become minus integral. The cosine x will hang out for a moment. The sine we're going to call u squared, and the dx will replace by du over cosine x. That will account for that extra cosine, and so we have minus integral of u squared du. We can use our power rule and get minus u to the third and then a 1/3 in front. And so finally, bringing that sine x back down, minus 1/3. The u we said was a sine x, but that's sine cubed x plus c. That is our integral. Okay, now the yellow one is tricky because we have these different powers that can confuse the issue. So when you see something like, it looks like the inside function to me ought to be what's in the parentheses, and that's actually correct. So let's start with that and then see how clever we have to get. So if u is the x squared plus 3, then du is going to be 2x dx. So the dx is going to be du over 2x. Okay, well, let's see what this does. we've got this x cubed that we're going to, hopefully we can get that figured out. Now the x squared plus 3 to the fourth is going to be u to the fourth. The dx we're going to replace by du over 2x. Well, that doesn't look like it's enough. That accounts for one of those x's, but it doesn't account for the whole x squared. So where we are now, if we pull that 2 out, it's a 1/2 integral of x squared over u to the fourth du. Well, we can't integrate when we have the x's remaining with our u's. So if you look at that, maybe you see it, that back here in our original substitution, we can solve that for x squared and see that that's actually u minus 3. This is great news because that will make us change this integral into u minus 3 over u to the fourth du, and we don't have any more of those lingering x's that were getting in the way of us integrating with respect to u. Now, there's still another clever thing to do. We're going to split up our fraction and call that u over u to the fourth minus 3 over u to the fourth du. Then we can further simplify that and call that 1 over u to the third, which for integral purposes I'm going to think of as u to the negative 3. I'm going to go minus, I'm going to bring this 1/2 and give this its own integral. The 3 I'm going to pull out, so that's 3/2. You with me there? Minus 3/2, and the over u to the fourth is going to be a u to the negative 4 du. Okay, now we're making progress. So using our power rule, we'll add 1 to the negative 3. That will become a negative 2. We need its reciprocal, and we already have that 1/2 in front. So that's going to be a negative 1/4 u to the negative 2. I'm going to come back to that in a moment. We got the minus 3/2 hanging out. We're going to add 1 to the negative 4 and multiply by its reciprocal. And so it looks like those 3's can cancel for us. And so that's going to be the negative times negative is a plus 1/2 u to the negative 3 plus c. So now you get a choice. I mean, you can leave those as negative exponents. Remember, our u was that crazy x squared plus 3 over here. So we could call that, and that would be okay, to call that x squared plus 3 to the negative 2, and a 1/2 x squared minus 3 to the negative 3 plus c. That would be perfectly okay, and that might be the easiest way to go. It's been a long problem already. Or if you wanted, you could call that 1 over 4 times x squared plus 3 and make the positive 2 be in the denominator, and 1 over the 2 and the x squared. That was supposed to be a plus 3, I think, wasn't it? Yep, so somehow I lost the plus on that. Plus 3 to the third plus c. That's just an alternative. There's no advantage to one over the other. All right, this is tough stuff, but it's stuff we're going to make a lot of use of going down the road here.